Good day, my friends. How are you all doing? I hope you're doing great today. It's bright and sunny outside my window, and it's a nice day outside. I hope you're also having a nice day so far. So, today we will continue our lecture on chance, how results of an experiment of a trial like tossing a coin happens by chance. We do not know what's going to happen. Now, in statistics, chance is known as probability. Okay, so we are going to take a hard look at probability today, and I will explain it in easy terms. What does it really mean? What does probability really mean? And we are going to take a look at it. So please hang in there. Please do not quit right away. Please stick to the end of the presentation where I will give you some important tip at the end of this program. So with this, I'll share my computer screen with you. Definition of probability. As you all know, probability means a chance of certain things happening. Okay. For example, when you toss a coin, a fair coin, I should say, you expect in the long run you'll get 50% head and 50% tail. So the chance of getting a head in the long run of tossing coin is 50%. Okay, so that's the beginning lecture or beginning to the idea or start to the idea of probability. Okay, it's what percentage of the time certain event will happen in the long run. For example, if you toss a coin 10 times, do not expect 5 heads and 5 tails. That's not going to happen. Okay. So, classical approach to probability for equally likely outcomes. So, probability of an event E is represented by capital P in parenthesis capital E. Is any event, for example, like my example, what is the probability of getting a head H? E then becomes H because head is H. Probability of getting a head. Number of outcomes favorable to E divided by number of outcomes in the sample space. What is an easy way of understanding this? Okay, think of probability of head in the long run. We know each coin has two faces, so that number 2 will go in the denominator. In the numerator, we are looking for how many of those two faces have head, and that's only 1. So probability of head is 1 out of 2. Why? One face contains head. There are total two faces. So 1, the smaller number is in the numerator. The larger number, 2 faces, 2 is in the denominator. 1 out of t. 2, probability of head in the long run is 0.5. So probability is usually expressed as a decimal, 0.5, or as a percentage in case of probability of head in the long run, 0.5 or 50%. Okay. According to this definition, calculation of probability consists of counting the number of outcomes that make up an event, counting the number of outcomes in the sample space, and then dividing. Or in simple way, one face containing a head, 1 goes in the numerator, divided by total number of faces in a coin, 1 out of 2 or 0.5, 50%. 4 students, Amit, Bettina, Carlos, and Dara submitted. Let me move my picture. Okay. Submitted correct solutions to a math contest that had two prizes. Amit and Bettina are math majors, and Carlos and Dara are statistics majors. The contest rules specify that if more than 2 correct responses are submitted, the winners will be selected at random from those submitting correct responses. You can use A, B to denote the outcome that Amit and Bettina are two selected. The other possible outcomes can be denoted in a similar way. Then the sample space for the outcomes, for the chance experiment of selecting two winners from the four correct responses is A and B answered both the questions correctly. A, C, A, D. Remember, each of these letters indicate the name of one student. A, D, B, C, B, D, or C, D. So recount the total number of possibilities. Is AB1, then AC2, and so forth. 1, 2, 3, 4, 5, 6. There are 6 possible combinations. Okay. Because winners are selected at random, the 6 outcomes are equally likely, and the probability of each individual outcome is 1 out of 6. What are they saying? 6 possible outcomes. Each event, events, the winners are selected at random. So each possible combination has an equal chance of getting selected. 6 possibilities. So each of them has a probability of getting selected is 1 out of 6. 1, each combination, divided by 6 total number of combinations, 1 out of 6. Suppose E denotes the event that both selected winners are same major. A and B are a math major, C and D are statistics major. Both of them same majors. These are the only possible combinations. In that case, the probability of E is 2 out of 6. Why 2? Because there are two possible combinations in which both of the students have the same majors, A and B math major, C and D stat major. Two possibilities, out of 6. 2 out of 6. Or probability, as I said, is expressed in decimal 0.333, sometimes percentage, but usually using calculator, it's good idea to represent probability as a decimal 0.333. If F denotes the event that at least one of the selected winners is a statistic major, one of the selected winner is a statistic measure, then F consists of all outcomes, okay, except A, B. Why except A, B? Because in A, B, A and B are both math major. In all other possible combinations, look at AC, AD, BC, BD, CD, okay, there is Hmm. Uh, at least one stat measure. So there are 5 combinations AC, AD, BC, BD, and CD in which there is at least minimum one stat measure. Who are the stat measures? C, D, and D. Okay, so in all 5 of these, there is one stat measure. So the probability of that selection is 5 out of 6 or 0.833, 83.3%. Okay. We, the partner, discuss the following. Be prepared to share your insights with the class. Why might it be misleading to say that if a student is selected at random from the population of students at a 4-year college, the probability that the selected student is a freshman is 1 out of 4. As you know, we have freshmen, sophomore, junior, and senior. The what is wrong in this argument? Why the probability of freshman is not equal to 1/4? Why the probability of senior students is not equal to 1/4? Because if it had been 1/4, that means all the classes, that means freshman, sophomore, junior, senior, all the number of students in all of these grades, freshman, sophomore, junior, senior, are equal. That's not true. Okay. Freshmen may be higher in number, sophomore count may be lower in number. So you cannot say the probability of freshman is equal to probability of sophomore is equal to probability of junior is equal to probability of senior is equal to 1/4. That is not true because the number of students in each student class, freshman, sophomore, junior, and senior, they are not equal. The classical approach to probability works. So we are now going to discuss how we are going to find these probabilities in certain situations in life. such as, I'll give you an example. Like we already discussed about tossing a coin. That is a prime example of classical experiment, because classical means the results are not going to change. There will be always two faces in a coin, one out of two. One face is head and another face is tail. Probability of head is half, probability of tail is also half. The classical approach to probability works well for chance experiments that have a finite number of outcomes that were equally likely. However, many chance experiments do not have equally likely outcomes. Okay, equally likely outcomes, you understand? Equal chance of happening. For example, consider the experiment of selecting a student from those enrolled at school and observing whether the student is a freshman, sophomore, or junior or senior. If there are more seniors than sophomores at the school, then the four possible outcomes for these chance experiments are not equally likely. Like we discussed here before, the number of students in each class, freshman, sophomore, junior, and senior, they are not going to be equal, most likely. Therefore, you cannot say that probability of senior is equal to 1 out of 4. It will be what? It will be number of seniors in this college divided by total number of students. So the probability of each of these class, freshman, sophomore, junior, and senior, they're not equal to 1 out of 4. They do not have equal likely chance of happening because the number of students in each class is different. So we are going to use a relative frequency. So the question now becomes, what will we do if the probabilities of events are not equally likely? Different events are not equally likely. So as you noticed in this case, what we did was we counted the number of students in each category, freshman, sophomore, junior, and senior, in each category, added them together, got the total number of students from the four categories, freshman, sophomore, junior, and senior. That goes in the denominator. Then if we want to find out probability of a senior student, we'll take the number of senior students in the numerator, small number, divided by total number of students, the large number. That will give us the probability of selecting a senior from that college. Okay. So that's a kind of a relative frequency. Relative frequency, as you know, is how frequently a category occurs. We discussed that all before, how frequently a category occurs in a combination of events. So, for example, if there are 300 senior students out of 1,000 students in a college, probability of senior is 300 divided by 1,000 or zero point 0.3. If there are 400 freshmen, then probability of freshmen is 400 divided by total number of students, which will be constant, which is 1000, or 400 divided by 1000, or zero point 0.4. When any given chance experiment is performed, some events are relatively likely to occur, whereas others are unlikely to occur. For a specified event E, the probability that a value that gives information about how likely it is that E will occur. So basically they're saying probability of an event E gives you a percentage or chance of that event happening. Sometimes it is expressed in decimals. In relative frequency approach to probability, the probability describes how frequently event E occurs when the chance experiment is performed many times. Like I said at the beginning of this lecture, if you toss a coin at 10 times, you're not going to get 5 tails and 5 heads. Why? Because the number of tosses is too few. However, if you toss the coin 5,000 times, quite likely you will get close to 2,500 times heads and 2,500 times tails. Okay, so relative frequency approach will be probability of head is 2,500 divided by total number of tosses, 5,000 is 0.5. Long term probability. It's a relative frequency approach. That means out of the total 5,000 tosses, what percentage or how frequently head occurs, which is 2,500 out of 5,000, which is 0.5. Frequently, a coin is described as fair. It is said that there's a 50% chance of a coin landing heads up. What is the meaning of the expression fair? It cannot refer to the result of a single toss because a single toss cannot result in both a head and a tail. Might fairness and 50% refer to 10 successive tosses yielding exactly 5 heads and 5 tails? Not really, because it is easy to imagine a fair coin landing heads up only 3 or 4 out of 10 tosses. Consider the chance experiment of tossing a coin just one. Define the simple events. H is the event that the coin lands with its head side facing up. T is the event that the coin lands tail side facing up. So, now suppose that you make a fair coin, take a fair coin and begin to toss it over and over. After each toss, you calculate the relative frequency of heads observed so far. This calculation gives the value of the ratio, number of times the event H occurs divided by total number of tosses. Okay, so on the top row you have the toss 1, 2, 3, 4, 5 going all the way up to 10. And then the second row of numbers 0, 1, 2, 3 is number of heads. Cumulative means including that particular toss and the one before it. For example, for toss number 2, you got 1 head. For toss number 1, you got 0 head. So cumulative number of heads up to toss 2 is only 1. Okay. Next one, you also got a head when you toss the coin 3 times. So uh, it will be 1 plus 1, cumulative will be 2, and so forth. So what do they have in the last row of numbers, relative frequency? You're taking the cumulative number of head and dividing by number of tosses. 1 out of 2 is 0.5. Next one is 2 out of 3 is 0.667. Next one is 3 heads out of 4 tosses, 0.75. Why are they calculating this last row of numbers? They're showing that the proportion of heads will vary all over the place, starting from 0, and then finally it might take a while to stabilize it to 0.5. Ideally, you would want 50% head, 50% tail, so relative frequency of head should be 0.5. But as you see from the last row of number, focus on these numbers 0.667, 0.75, 0.6, 0.5, 0.571. You can say they're all over the place, they're not really exactly 0.5 except in a few cases. So here is a picture of the same situation. The horizontal black line is drawn at a vertical distance of 0.5 from the x-axis or the horizontal axis. So the black line in the middle of the diagram is 0.5. Its value is 0.5. It is the relative frequency of heads, or it is at a distance of 0.5 from the horizontal axis. Okay, and blue is the relative frequency of heads in real life. And as you can see, most of the time the relative frequency or the blue dots are above the black horizontal line, which is the theoretical probability of a head should be 0.5. That does not happen if you toss the coin 50 times. The probability is not really 0.5, it's slightly above it. So what is the difference between the left diagram and the right diagram? Only difference is if you look at the horizontal axis, here the number of tosses. In the first one on the left, you toss the coin 50 times. On the one on the right, you toss the coin 1000 times. And look at the blue dots. Now, when you are tossing the coin so many times, you are approaching the theoretical probability, which is 0.5. We all know the probability of getting ahead is 0.5. But in the long run, what is the long run? You have to toss the coin more than 50 times. You have to toss the coin somehow in this picture, somewhat like somewhere like 1000 times before you get almost 500 heads and 500 tails. So this is called law of large numbers. In simple language, what does it mean? As you saw in the probability experiment, that if you repeat an experiment many, many times, the probability of an event, and in this case head, in our example, will approach its theoretical probability, which is 0.5. So law of large numbers means large number of repetitions of a chance experiment. Repetitions means you're tossing the coin many, many times. Relative frequency approach to probability. The probability of an event denoted by P parenthesis E is defined to be the value approached by relative frequency of occurrence of E when a chance experiment is performed many times. If the number of chance experiment is performed is quite large, then probability of E is given by number of times E occurs divided by number of times the experiment is performed. What does it all mean, this equation? It means think of tossing the coin 1,000 times. 1,000 comes in the denominator and you count the number of heads you get in the 1,000 toss. Most likely it will be close to 500, maybe 495, 496, but it is still very close to 5, and that is the theoretical probability of getting ahead. Think about it, 495 out of 1,000, 495 heads out of 1,000 tosses is 0.495, which approaches the theoretical probability of 0.5. Okay. So probability can be a personal measure also. The previous approach was doing the experiment and finding the relative frequency of the event in the long run. That gives you the theoretical probability. Like the probability of head in the long run is 0.5. But sometimes it can be a personal measure of strength of a belief that a particular event will occur. For example, probability of 1 means the person is 100% sure that that given event is going to happen. If, on the other hand, the person believes the event is definitely not going to happen, like looking outside today is sunny. So if I say probability of rain today is 0, what does it mean? No chance of rain happening. It's 0% chance. So the highest probability will be 1, the lowest probability will be 0. And probability of an event is anywhere between 0 and 1. As I said, it is expressed as a decimal or a percentage. But the example before is subjective probability. What does it mean? It is based on a person's own personal belief. There is no scientific basis. There is no measurement happening here. Therefore, there are challenges with subjective probabilities. Okay? They have limited use. So there are three approaches to probability. One is the classical approach. You toss the coin 1,000 times, you get 495 heads. So probability of head is 0.495. 495 times out of 1,000 times. What is subjective approach? It's your own belief. Is it going to rain today? No. I'm thinking it's 0. Okay. But not much use. The best is the relative frequency approach, where you conduct an experiment a number of times, like tossing the coin 1,000 times, and see how many heads you get. Number of heads divided by total number of tosses is the relative frequency of percentage of heads in the long run. Okay, so I'm going to stop here today. What did we learn in this section, if you ask me? We learned what is the definition of probability. It's a chance or percentage or probability of something happening. The lowest value of probability is 0. The highest value is 1. When the probability of an event is 0, it is not going to happen. When the probability of an event is 1, we are 100% sure that the event is going to happen. Probability of rain today is 0. Sun is blue sky. On the other hand, probability of sunny is 100%. Okay. Problem with subjective approach, that is my own belief, is no good. There's no scientific basis. So the best approach is to use the relative frequency approach, where you conduct an experiment many, many times and look for the particular event that you are interested in. Example, toss the coin 1,000 times. How many times out of those 1,000 times you got head? 495 times. Then your probability of head in the long run is 495 heads out of 1,000 tosses is 0.495, which is close to the theoretical probability of 0.5. So that's where we will stop today. If you have any question or comment, please write me a note. And if you like this video, please give me a thumbs up. I'd really appreciate that. And also, please let me know, where are you watching my video from? Do you have any questions? Do you want me to answer any questions in my future videos? I'd appreciate a feedback from you. Really, I mean, really. And if you like this video, please share with your friends. You and your friends, please subscribe to my channel by hitting the red subscribe button. I'm making a lot of these interesting videos. I want you to learn to expand your knowledge. If you have questions, please feel to ask me anytime. I'll answer as soon as possible. And please subscribe to my channel by hitting the red subscribe button and let your friends know about my channel. I appreciate that. And please stick around and watch the video the entire length. I would appreciate that. Like in this video, I gave you some important tips at the end of this video. So again, thanks for watching, and please do not forget to watch me tomorrow when I'll be back with another interesting presentation. Thanks for taking the time and watching the video. Take care. Have a nice day, and I will see you definitely next time.